And let's start by rehearsing what's the definition of this expansion using our binomial coefficients, using our NCR and that kind of thing. Okay. The first term, right? If I've got A as the first term of the binomial, B is the second, right? It's going to be A to the n, but how many lots of A to the n are there? Think back to Pascal's triangle and how we rewrote it. It's going to be n choose 0, right? It's always going to be n choose 0 because you start off by saying, I mean, this coefficient has to be 1, right? And so it's going to be how many ways can I choose 0 out of n, because otherwise it'd be, you know, a bigger number. Okay, now when you go to the next one, what you've got is n choose 1, so that just increments up, okay? Your power of n is going to drop down 1, right? And your power of b will increase. And really, actually, there's a b to the 0 hiding there, which is just 1. And then the trend continues. Okay, does that make sense? Now, how does it finish off? Because this is a finite series, right? Hence finite series. Where does it end? Let's do the second last term. Okay, it's still going to be n choose, but what am I going to be up to if I'm at the second last term? N minus 1, right? Which, by the way, is the same as n choose 1. Do you remember that equidistant relationship we looked at yesterday? What are we going to have here? How many lots of A will we have? This is the second last term, so just the 1, right? And we'll have n minus 1 lots of B, and then our very last term, n choose n, all the A's are gone, and you're just left with B. Okay? Great, so far so good. Now, the most useful, or one of the most useful kinds of A and B, it's kind of an interesting, simple combination. It's treating the A as 1 and the B as x. Okay, now that might seem kind of arbitrary to you, and also why don't we put the x first? All will be revealed, so hold on. How does this expand though? Okay, let's think about this. These coefficients are all going to be the same, okay? Because what the coefficients come from is just the power, right? So I'm going to have n choose 0, I'm going to have n choose 1, n choose 2, and so on, okay? What am I going to have as the other parts of the term, apart from the coefficient? Well, here I have 1 to the power of n, right? And no lots of x. This next one here is going to be 1 to the power of n minus 1. And how many lots of x? We've got 1 this time, right? Plus, this will be 1 to the power of n minus 2, 2 lots of x, and so on. Now all the way up onto the end, okay? So this is going to be the same coefficient, 1 lot of 1, that many lot of x's, and then the very last term, no lots of 1 and that many lots of x, okay? Now I wonder if you can see why we put the x second rather than first, even though so far we've put the x first. Because what this is, all the 1 to the power of whatever, okay? They're all just 1, yes? So I can actually get rid of all the 1s from out of this series, okay? So this is n choose 0 plus n choose 1. I don't need to put the 1 there because it's redundant, really. Lots of x. N choose 2, lots of x squared. Might just stick in another one just for the sake of it. N choose 3, lots of x cubed. And you can see that this term down the bottom of the NCR, right, the R, that corresponds to the power of x that you've got. Right? Can you see that? Okay, so the reason why I put the x second is because what I get at the end now, this series here, that's the way we ordinarily write GPs. Right? This is GP. Okay? All right, now, file that away in the back of your mind, and you may like to get out either this sheet, oops, and have a look at the bottom of the page. There's a whole bunch of things with sigma notation. And also, I'm going to do 2 or maybe 3, depending on how time goes, of the questions out of the program which introduce sigma notation. This line here, right, this line, because it's just a GP, okay, this is prime material for writing it in sigma notation, okay? So the first thing I would say is, how many terms are there in this series? I started at 0 and I ended at n, okay? So there are n plus 1 terms. The way that I would count that up is I'd say let's start from 0, because that's my first one, and then I'll go up to n, because that'll be my last one, okay? Now, what's the thing that goes in here? What's the function that actually gets evaluated as the thing goes up? Well, as r increments, I'm going to have n choose r, right? So I start at 0, 1, 2, 3, and so on, okay? But then I also have this x term to deal with, okay? It's x to the power of r, right? This number and this number always match up, exactly, okay? That's how I built the series. Okay, so this here, might stick it in color. This is a crucial identity to get, okay? It's a really nice, this is why it's handy that we learnt sigma notation under series of sequences, because it's way better to write this than this previous line, okay? Right, now let's go to the program and see how there are some examples of how we actually use this. So I think this is under point 7 in the program. It says prove finite series. That's where the name comes from. And given this result, so this is a given. You can quote that. Okay. Let's prove this. This is the first one. What you're required to prove is r equals 0 all the way up to n of this equals that. Okay. So just have a look at it first. Now, if I hadn't told you any of this before, and even having told you, when you look at this the first time, thinking about it as an identity, we tend to go from, when you got left-hand side, right-hand side, you think, start from the complex side, and then go to the simpler side, right? Does that make sense? Because our brains tend to simplify better than they make things more complicated, okay? So instinctively, you go from this side to this side, right? Probably, okay? Because this is a whole bunch of things, and we would probably expect that in some way you're going to simplify out, and it will come down to this, okay? I'm going to save you 15 minutes now. It won't, okay? Not unless you're aware of this, okay? So in fact, I'm going to start with the right-hand side. This is a bit counterintuitive, isn't it? I wonder if the cogs are turning, you can see the relationship to what we just established up here. Start at the right-hand side, which is 2 to the n, okay? Now, how can I relate this to this result we've just shown? Which does it look more like? It looks more like this side, right? In the special case where x is equal to 1, right? So what I've got here, this is 1 plus 1 to the power of n, right? And so now you can see where the binomial expansion comes in, right? Because this here is a proven result, I can say that's equal to r equals 0 up to n of n choose r. Now, x to the power of r is really 1 to the power of r, because I've chosen x equals 1 in this case, okay? So 1 to the power of r. Even though, again, it's trivial, it's important that you include it so you understand where this came from, okay? And from there, well, that's basically it, isn't it? That's all I was asked to prove.